HanselMinutes.com. It's Hansel Minutes, a weekly discussion with web developer and technologist Scott Hanselman. This is Lawrence Ryan announcing show number 416, recorded live Thursday, March 20th, 2014. This episode of Hansel Minutes is brought to you by Telerik, empowering over 1 million developers to create compelling app experiences across any screen. Learn more at telerik.com. And by Franklins.net, makers of GesturePak, a powerful gesture recording and recognition system for Microsoft Connect for Windows developers. Details at gesturepak.com. In this episode, Scott talks with Andrew Gerrand about the Go programming language.
Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and I'm chatting with Andrew Gerrand, who is a developer on the Go team at Google. How are you, sir?
Good. How are you?
I'm lovely. Thanks so much for taking the time to chat with me today, all the way from Sydney. So I want to understand where Go as a language fits in. Like, there seems to be a renaissance of languages right now. Everyone's making a new language. Every time I go to Hacker News, there's a new language coming out, and Google's got Dart and they've got Go. I understand that there was a time at Google where there were only a few languages allowed, right? You had a very limited number of languages to choose from. Wasn't it basically Java and C++?
Sure. I mean, I think maybe that's a slight exaggeration. Like, people have been creating languages pretty consistently for pretty much since computers have been around.
Okay.
But so on the Google angle, we actually still only have a very small number of languages that are usable by the general engineering population. And they are C++, Java, Python, and Go. And of course, we use JavaScript for front-end stuff.
Of course.
But those four are considered the canonical languages. And we also have a couple of sort of domain-specific languages that we've developed inside of Google. There was Sawzall for logs processing, which is also being used by some people outside. And we have a language for specifying monitoring configurations and machine configurations and so on. So Google's always been a place where we've been unafraid of creating new languages. So it's kind of natural that we should see a couple coming out. What's interesting about Go and Dart is that they're open source projects that Google is effectively sponsoring and putting a lot of engineering effort behind. And so they're not just for Google to use, but they're really for everyone to use. And we sort of hope that, particularly in the case of Go, that we can kind of, I guess, philosophically reboot some people's assumptions about what's necessary and expected from a programming language. And so what do I mean by that? Well, one thing that people, when they look at Go, well, should I talk about what Go is in general? Just as
let's talk about that. Like, Go is a language that solves what problem? Like, why Go and why now?
So to give a bit of background on where Go came from, it was developed by a small team of people, Rob Pike, Ken Thompson, and Robert Griesmer, who were engineers at Google and had been there for, I guess, 5 or 6 years at the time. And this is when Google was about 6 or 7 years old. And so they were accustomed to building services at Google, mostly in C++ and some Java, I guess. And Google is basically a large C++ code base and a pretty substantial Java code base, with Python and the other languages a distant kind of third and so on. But only a really small fraction of the services built at Google require the kind of control that you get with C++. Like, C++ is a fantastically powerful language, but it also requires you to think about a lot of stuff. It's also a very complicated language. And so even if you're writing something really simple, like a web app, for instance, or a command line utility or something like that, you still need to think about memory management, and you still have to deal with many, many aspects of the build system and language and so on. That, you know, if you're using Python or Ruby or something like that, it's a lot easier. You know, you can just, those dynamic languages mean you don't have to think about the type system, and you can just kind of write what you mean, and then it comes out and it works. But sort of in the culture of Google, where we used C++ for everything, and to talk to various services, you really needed to be using C++ libraries. You were kind of locked into that approach. And it was very hard to argue that you should use Python instead, because Python doesn't really give you control over memory. It's generally very inefficient. So it really limits what it's useful for, even though it is more fun to use. And so the question was really, can we have a language which is as easy and as fun to use as these newer scripting languages, but that still gives you enough control to do things, the sensible way, the efficient way. And so Go is that language. Go is basically, you could look at Go as starting off with C and taking away a lot of the dangerous manual memory management stuff, and then re-examining the type system and just putting in there what is necessary, and then adding some concurrency and adding a few other nice things. And so what you get is a language which is as fun to use as a scripting language, but it gives you type safety, it gives you, efficient runtime performance. And so it kind of sits in this middle ground between what we consider low-level system languages and, scripting languages.
What do you think it is that makes a language fun? I'm sure everyone has their opinion, and that's very objective. And I don't particularly find C and C++ fun. I certainly don't find C++ fun anymore. C++ represents frustration to me.
Yeah, I think a language is fun when you can think about something and then you can just write it out the way you think it should work, and that works. And fun is also being able to experiment quickly so that you can take something and, quickly change the way that works, quickly, try out a new idea, a new interface that you think might be better without having to go back and, go on some big yak shave refactoring mission to do that. Mm-hmm. And I guess, part of the reason why Go is fun is that it was designed for scale. It was designed for this to be working on really, really large code bases with really large numbers of programmers. And that design philosophy kind of caused us to put less complexity into the language itself. So it has a much smaller set of features compared to most mainstream languages. And as a result, you can really look at any code and really understand what that code does, even on a superficial reading. So you don't need to have a lot of context to really understand part of a system. And that property for working in the large translates really well into fun in the small. So if you're working on your own personal project, if you decide that, you want to fundamentally change the core interface of your program, it's just a bit of search and replace that's required. It's not a full-on you don't have to go around and fix all your inheritance hierarchies or whatever. So that's kind of on the type system side. The thing that makes it fun in another way is that its concurrency system lets you model concurrent problems, which are generally the type of problems we deal with in networked environments, like writing web applications and so on. And it lets you deal with them in a pretty natural way, and a way that's generally safer than the approaches that you might take in sort of more traditional thread-based environments.
Is it from a concurrency perspective? It introduces a number of concurrency-related syntax and types to support that. Is it up-leveling things, or is it just taking the knowledge of the last many years of people trying to solve these concurrency problems and, like you said, paring it down to just what is needed?
Well, Go's concurrency approach is inherited from a series of languages that Rob Pike worked on at Bell Labs. Among them are NewSqueak and Aleph, and they had a CSP-based concurrency model, which is a message passing concurrency model, which I guess people would be kind of familiar with from Erlang, but Go's take on that is a bit different.
Mm-hmm. And CSP is communicating sequential processes, just for folks that may not know that.
Yeah, that's right. That's
also known as channel programming, right?
Yeah, exactly. So Go's approach to concurrency is at a language level. It's not a library support level. It's basically, you can write a function or a function closure, and put the keyword Go in front of it, and then have that run in another thread. Well, I say thread, I actually mean a Go routine, which is a kind of lightweight thread, like a green thread, managed by the Go runtime.
So it's not a thread, like you use the term green thread, which I think of in terms of Java. That's like a real thread and then a pretend thread.
Yeah, it's definitely a pretend thread. Mm-hmm. In the sense that a Go program will typically spin up, only as many threads as are required to keep all the cores humming along. But otherwise, the Go program and the Go runtime has a better understanding of the scheduling needs of the program than the operating system. So rather than pushing all that work onto the operating system by using operating system threads, it just schedules the execution of these Go routines across a smaller pool of OS threads. Mm-hmm. And the end result is that you get the kind of performance that you get from, say, Node.js when you have to write in a non-blocking callback-oriented style. But you get that kind of performance in Go, but you get to write blocking code. So you just write the code that blocks, and the Go runtime knows that those are blocking events, and so it just puts that Go routine into the background while it's waiting on some disk I/O or network I/O or whatever, and then it executes whatever the next waiting Go routine is.
So is this specific to I/O, or because there's the idea of running something on a background thread so as not to block things, and then there's the idea of doing something asynchronously and letting some I/O completion port handle it and let me know when it's done. Is this something you can do with CPU intensive things, or is it only things where you're writing to disk or talking on a wire?
No, it is possible to do it with CPU intensive things as well. You can, obviously, if you have more concurrent CPU intensive things going on than you have cores to spare, then some of those processes are going to be starved. But in general, the Go routine scheduler is a bit preemptive now. It used to be totally cooperative, but now it will preempt other threads. So you can just run, many parallel computations, and the runtime will just sort it out. Generally, I think the scheduler is aware of the network, so it's fairly tuned towards network servers, so that it can know, this Go routine's waiting on this socket, and so I know when this socket when a message on this a write on this socket is ready, that I will wake that Go routine. Like, that's kind of built into the core of the scheduler. So it's definitely more oriented to doing I/O stuff. But there's no reason why it's unsuitable for doing computations.
So how does that differ with Erlang? Because Erlang also prides itself in the way that it handles concurrency, but it's a little bit different than the Go model.
Yeah, so there's a fundamental difference between Erlang and Go in a program design kind of sense. So in Go, you write a program that is compiled to an executable, and then it runs as a process. And all of the concurrency stuff exists within that process. So you create Go routines, you communicate between them with channels. But it's all going on inside that one process. If you want to communicate between processes, then the expectation is you have some kind of infrastructure to do that, like an RPC system, some kind of name resolution system, and so on. And we have those things inside Google. There exist other solutions for that outside of Google. But in Erlang, they have this really powerful VM system where Erlang processes are much smaller, and a typical Erlang program will consist of many of these processes that communicate through message passing. And in an Erlang program, the expectation is that any of those processes can fail at any time, and you design your program such that you expect these things to fail and you gracefully recover when messages aren't delivered and so on. But in a Go program, the other Go routines must be running because you're all running within the same process. And so if you send a message to another Go routine, that message has been received because you're still alive, speaking from the Go routine's perspective. And so those two kind of represent fundamentally different ways of thinking about concurrent programming, I guess. One of them is, you expect things to fail and you just plan for failure all the time, whereas the other is you kind of program with the expectation of success within a single process. And so they're really, even though the message passing property is common to Erlang and Go, the way you use each language is really very different. And the runtime performance of both is quite different. And, the deployment story is obviously very different. With Go, you just ship a single statically compiled binary and run it. With Erlang, you have to set up your VM and so on, and administer that. And there are positives and negatives, I think, to both approaches. But Go is a much more traditional approach in the sense that you write a program that runs as a process on a machine somewhere. And then if you need a cluster, then you run many processes. But, you need to build out the infrastructure between those things. Erlang kind of gives you that stuff for free, but then it also locks you into that model as well.
Mm-hmm, mm-hmm. So we may not have explained kind of fully what the kind of runtime environment is. I mean, when we think of runtime today in 2014, I think people think about virtual machines and Java VMs and CLRs and things like that. They're not used to thinking about runtimes in the context of like the C runtime. Is Go running in a virtual machine, or is it more like C, where it is its own universe?
No, so Go programs are just compiled to statically linked binaries that are machine code. Mm-hmm. And so there's no VM. It's not interpreted in any way. When I speak of the runtime is essentially a object that's linked into that binary that does things like memory management and the scheduling of Go routines. While it's a part of every Go program, it's not something that runs a Go program. It's more like something that facilitates a Go program, if that makes sense. It just kind of does the things the Go program needs it to do. It's like a base foundation library in a way. In that regard, the fact that Go is compiled to machine language, there's a really nice property that when you write some Go code, and then if you look at that assembled machine code, the assembly code there is actually really similar to the Go code that you wrote. There's not these kind of levels of indirection between the code that you write and the code that's executed on the CPU. And so as a result, you actually it feels like you have a lot more control over what the machine's actually doing when compared to using interpreted languages or machine languages that run on a VM.
Can you drop down any lower? Is there like the metal, or is Go on the metal? Like, can I call C libraries easily?
Oh, yeah. So for one thing, you can write assembly as part of your Go packages, and it will just get linked in. So you just write your function specification, and then you have an assembly file that implements that function. And that's quite easy to do. If assembly is a bit too low level, you can just link against C code. There's a tool called CGO or CGO. And it's quite nice because the mechanics of it are pretty clever. You just write a normal Go file and you import a magical C package, like with a capital C. And you put a comment above the import declaration, which actually contains the C code you want to link into your Go code. So you have your C include lines, any C type declarations or function declarations that you might need. And then in the Go package, you can refer to any of the names in the C namespace just by saying c.foo, where foo is some name that exists in your C libraries. And there are a bunch of helper functions for converting between Go types and C types. And so writing Go wrapper libraries for C libraries is really straightforward. You don't even really need to be a C programmer to do it well.
And so Go apps make no promise to be portable, right? If I'm going to be doing things like C library linking in and inline assembler type things, would I compile to a particular distribution of Linux or compile to Windows, and then that Go program only works on that operating system?
Actually, Go is quite portable. If you only use Go, the language, if you only use the base Go distribution, so the basic standard library and so on, we've gone to great lengths to make sure that you can use the same standard library on Windows, on Linux, on OS X, and our other supported platforms. So while it's not compile once from run anywhere, it is write once and then compile to any of those targets. When you introduce assembly, obviously, if you only provide assembly for 64-bit Intel processors, then it's only going to run on those processors. But it's very easy. We have a nice convention for providing alternate implementations for different architectures. So if you know the assembly for ARM or 386, you can write that. But when it comes to C libraries, it's a little bit more complex. The short story is that if you're using a C library in your Go program is only as portable as that C library is. And so recently I've been working on an audio synthesizer project, and I'm using a library called Port Audio, which is, it's Go Port Audio, which is a Go wrapper around the C Port Audio library. And Port Audio is, as its name suggests, a portable library for talking to audio interfaces, like your sound card in your computer. And that actually runs on OS X, Linux, and Windows, because that's where Port Audio runs. And yeah, it just works. So it can actually still be very portable, even though, you are dealing at a lower level than some other high level environments.
Nice. It is as portable as what you're using is portable. That's cool.
Yeah. It definitely doesn't get in your way.
One of the things I thought was significant about Go from a getting mindshare perspective is that the famous author Bruce Eckel, who was on the ANSI Standard Committee for C++, and he wrote Thinking in C++, has said that the complexity of C++ is no longer justified vis-a-vis productivity. He says all the hoops that you have to jump through and all the hassle is a waste. So here's someone whose, career is on all about C++, who's saying that, Go makes more sense for the class of problems that C++ was intended to solve. I wouldn't disagree. I think there are a lot of people, obviously I'm biased, but I think there are a lot of people who, are really good and proficient at C++ and it works for them. But I think, on balance, there are fewer and fewer problems that C++ is really well suited to today, given the alternatives that exist. And I think Go is one of those alternatives for sure. What is a class of problem at Google or that you've worked on where Go just really slid in and was just the perfect solution, and doing it in Go was so much more of a joy than it would have been had you done it in another language?
One example that jumps out at me is there's a download server that serves dl.google.com. So it serves all of our Android and Chrome and Google Earth and other big kind of binary downloads. And so basically it's a static file server, but it's a little bit more complicated than that because there's a whole lot of business logic that dictates, which files should be served where and when. And also it needs to talk to our back-end storage system. So it's obviously, you can imagine, we don't just have the files sitting on a ext2 partition somewhere on some Linux box. We have our distributed storage system. And so we have this, the architecture of the download server is basically, there are many of these processes running across several data centers, and when a request comes in for a particular file, it will fetch that file from the backend storage system and serve it out to the client. But it also does a level of caching where within a given cluster, these processes kind of form a distributed cache together, caching chunks of each of those files. And then each of the processes also has in it a hot cache so that any particularly in really high demand file will be cached in each process as opposed to across all of them. And so to make this work well, Brad Fitzpatrick wrote a library called Group Cache, which is now an open source project. You can get it from github.com/golang/groupcache. And it does all of that caching layer for you in Go. And the actual library itself is really nicely designed. It's a really nice example of using Go's interfaces to design really nice API. But basically, that project was a rewrite of a C++ program, and the rewrite really played to all of Go's strengths. It uses concurrency heavily, it uses interfaces heavily, and the end result was significantly shorter. I think it was like a quarter the number of lines. It was much more well tested because the first thing Brad did was write a whole lot of nice tests. And it ended up being really high performance. Actually deploying that, which happened quite a while ago, helped us find some hotspots in the runtime performance and the compiler as well, so that we could tune Go as a result of that experience. But that really came together really, really nicely. And there are other projects of Google in a similar vein, where Go has just slid in and really been a perfect fit like that. I could talk about another example, which is also open source, is a MySQL load balancing and sharding system called Vitess, which YouTube use very heavily. So if you load any YouTube page, it goes through this Go program. And that's a project that's been ongoing for a couple of years, and they're very, very happy with how Go has worked for that.
Yeah, this the one that Brad Fitzpatrick worked on, that it replaced not only Python and C++, but like you said, it got much smaller. It starts up faster. It was just a perfectly suited thing. There's a great talk that he gave at OSCON in 2013, and I'll put in the show notes. People can get that Powered by Go download.google.com slide deck where he goes through it and shows you examples of C++. Here's what it was in C++, and here's the equivalent code in Go. Look how much easier it is to read, and a lot less moving parts. It's pretty slick.
Yeah, and the group. There are other people outside Google now using that group cache library that we open sourced, and yeah, it's a really nice general solution to a problem that a lot of people have.
So where do people go, no pun intended, to check out Golang and work with it immediately, get started with it?
Visit golang.org. There's a download link on the front page. You can also take a tour of Go from there, or just go to tour.golang.org, and then you can learn Go from your web browser, and you can play with Go code snippets and run them from the browser and learn all of the aspects of the language effectively. Nice.
No download necessary to play with Go.
Yeah, that's right.
Very cool. Well, thank you, Andrew, for chatting with me today.
No, my pleasure.
This has been another episode of Hansel Minutes, and we'll see you again next week.